Thank you. Ooh. Hello. So today I'll be speaking very loudly. Yay, thank you. I'm going to talk today about NYTProf. Does anyone use NYTProf? Lots of hands, lots of hands. Okay. Has anyone never used it? Great. Okay. Hopefully I can persuade you that it's worth using. Has anyone used Devel DProf? Has anyone used it recently? Okay. So, Devel DProf is just so broken it needs to be deleted. Here's a little example. This little Perl code generates 1,000 subroutines that are all identical. And then you run dprof on it. And dprof says that it spent all the time in 4 of the subroutines. And what's happening here is that Devel dprof uses a very slow clock, and the clock went tick just when it happened to be in those 4 subroutines. So before I talk about NYTProf, I want to explore profiling in general. There's 2 sort of dimensions to measuring software performance. There's the CPU time, how much time was spent on the CPU, and how much clock time was spent. And then you can measure that in terms of subroutines, how much time is spent in a subroutine, or you could also measure it by statements. And which of these are more useful? So CPU time versus real time. The CPU time measures time actually executing your code, doing real work, and it's not much affected by the load on your system. Doesn't spend time waiting for I/O. And traditionally, CPU time has been used for a lot of profiling. But real time is kind of our time. It's real world time. It's how long you have to wait for something. So it is affected by the load on the system, but it includes the time spent waiting for I/O, waiting for the CPU, waiting for resources. On the statement versus subroutine, the problem with subroutine profiling measures the time between entering the subroutine and returning. That's the inclusive time, the time spent in that subroutine. It's reasonably fast because it doesn't have to do very much. It's only, the profiler is only involved when you're entering and leaving the subroutine. But old profilers, traditionally Perl profilers, especially dprof, have been upset by funky control flow where you're things like go to another subroutine used to confuse dprof. And it doesn't measure the time spent in the individual lines of the subroutine. So I'm thinking that this, I'm so used to giving this talk that this feels old to me, and I feel like NYTProf has kind of swept these issues under the carpet. This talk was written for an audience that I was trying to convert to NYTProf, and perhaps that still applies to some of you. Statement profiling gives you very fine detail of every single statement. But if you only have statement profiling, you end up with too much data. It's hard to see the structure of where the time is being spent in your program in relation to the structure of the program. So really what you need is both of them. You need subroutine profiling to let you focus in on where the time is being spent in terms of the structure of the program. And then statement profiling to show you where the time is being spent within the expensive subroutines. So Devel NYTProf has both, has a subroutine profiler and a statement profiler, and they're relatively independent of each other. It's possible to run NYTProf with one disabled or the other disabled, or use both of them together. Now, when you're profiling, NYTProf makes the code run about 4 times slower. Now that's actually pretty good. It's the fastest of the available profilers. All the other profilers make your code run a lot slower when it's profiling. Naturally, it uses a little more memory, but not too much. And also the process will context switch more often. There's an odd effect that non-closures are slow to create as closures. I don't know what's going on there, but I don't think it's significant for the measuring. So how do you run it? Very simple, Perl-D NYTProf. And that's the kind of the typical use. You could also use -m, Another way, if you can't influence the command line that's being run, say the Perl code is being run embedded in some other bit of software, you can use the Perl 5 environment variable. And you can set options through the NYTProf environment variable. So here I'm saying, write the profile to this particular file, and the add pib equals 1 means that every process will get its own output file. Now, if you're running a script that spawns a lot of Perl processes, it means you'll end up with a separate profile for every file, a separate profile for every process. CLCow donated the ability to take the data that comes out of NYTProf and run it through CacheGrind. I've not done this myself, but I believe it's useful. So if you're a CacheGrind user, then this is worth using. What most people do is NYTProf HTML, and you just run that command, or you can specify options to give a particular file name. What you get is a report, a big report with lots of pages, and this is the first page. And there's a lot of detail on here. You can see the summary of when the program ran, and the name of the program, and how long it took, and the number of statements, and so forth. And you can see links to the top subroutines. It's the top 15 subroutines here. And there's a link at the bottom that will take you off to a page of all the subroutines, and that's sortable. Most of the tables in the NYTProf report are sortable. So you can sort by inclusive time, exclusive time, or calls. And it also identifies xsubs and opcodes. Well, I haven't mentioned, NYTProf will profile some opcodes for you. So on this page, you can see there's this exclusive time and the exclusive time, so inclusive and exclusive. So exclusive time was the time spent just in the code of the subroutine. And the inclusive time is the code of the subroutine and any other subroutines that it called. I'll explain about that. So the way I use this is exclusive time is best for a sort of a bottom-up approach. It's kind of where time actually gets spent. It's useful for fine detail when you're looking at individual pieces of code that you're trying to tune up. But inclusive time is where I start. It's the first thing I look at. It gives you a kind of a top-down view of your application. So if you look over here, you can see the inclusive times. And what that'll do is, you can say, often a program will be structured in terms of several large phases. And what you can do is look at the time spent in each phase. So you might be pulling in some data, manipulating it, writing it out. So if you look at the inclusive time spent pulling in the data, manipulating it and writing it out, that'll give you a sense of, well, is it reasonable that I'm spending 10 times as long writing it out than I was manipulating it? And that'll give you a sort of a direction to look in. Okay. Now when you click on one of those subroutines, you'll get taken to a place like this. This is a little extract. And there's a lot of information here. What NYTProf has done is it's generated a report that embeds profile information as if they're comments in your code. That makes it very natural to look at. So you see it's telling you have comments saying that it spent so many milliseconds and then it's divided that down. So it's spent so many milliseconds within this function. And then those two numbers, the 39 microseconds and the 447, that's how much time is spent just in this function and how much time is spent in everything the function called. And then it breaks down all the callers. In this case, there's only one caller, and it tells you where it was called from. And then for the inside the function, for every place that calls out to somewhere else, it tells you how long it's spent calling out to that place. And then on the left-hand side, you can see the time spent on each line, and then the time spent in subroutines, time spent off somewhere else. You also get a tree map, and this turns out to be a really useful visualization of where the time is being spent. Now, this tree map is much more colourful than the one I showed you yesterday, but the colours don't mean anything at all. So, it's kind of, the colours are actually related to the packages, the namespace, but they don't have meaning. You know, green isn't better than red or vice versa. And as you move the mouse around, you get this tooltip, which is explaining, giving you more detail about what it is you're hovering the mouse over. And that'll make more sense. Oh, there we go. That'll make more sense when I show you an example. It's also possible to generate these visualizations of the relationships between the packages. Now it turns out that looks great, and for these little examples it works fine, but I can actually just show you one I did 10 minutes ago for... This is Perl Critic, and this is just the packages. This isn't subroutines, these are packages calling to other packages. So clearly that's not actually very useful. It's kind of pretty and makes a cute demonstration, but I wouldn't want to have to do anything with this except put it out and stick them on the wall. Okay. So you can get calls between packages, you can get calls, you can get graphs like this, but you can imagine doing this for Perl Critic. It would just be black. But for little fragments of code, it can be useful. Okay, oh look, time for a demo. So, literally 10-15 minutes ago, I ran Perl Critic on itself. Look, I can go like that. I ran Perl Critic on itself, just for the sake of giving me something to look at. Now, I did this last about 2 years ago, so I'm coming to this pretty fresh. I've forgotten everything I knew about Perl Critic, so I'm going to look at this as if I was coming to this for the first time and wanting to optimize it. So the first thing that stands out is pp-node find, and it's called 35, almost 3,600 times. So first thing I'd say is that reasonable? I know what I've asked the program to do. I would say, is that a reasonable number? Am I calling it too often? Now, it's often the case with profiling that instead of trying, or with optimizing, instead of trying to make some code faster, just make it called less often. Often the code is simply being called too often. So let's assume that it's being called the right number of times. I'll pop up another tab with that. Whoa, look, too much information. So here we are, defined. I can see, tells me here an ordered list of all the times it's being called. So I can say, oh yeah, look, it's being called from prohibit conditional declarations. And here's a link, and I can click on that link, and I can see, I immediately jump to the place that's calling this function most often. Okay. And here I can say, oh yeah, look, so look, there's find, it's being called from violates. So perhaps for some reason this violates function is calling it too often. And I can jump back. So this sort of, if you imagine a tree with a root, and you have a lot of branches coming in, and you have the trunk, and then a lot of roots going out. And what you're looking at here is all the places that called into this function, and what you're looking at here, for example, is all the places that this called off. And you can see it's giving you, this is a code reference, so you can't see what it's going to call, but NYTProf is showing you what it actually called, and how much time it spent making those calls. Okay. And then you see it made a bunch of calls here. So, and with method calls, again, it's telling you exactly which classes handled those methods. Now, it's interesting, this isn't the class that the invocant is blessed into. This is the class that actually had the method that handled the call. Okay. So, that can be useful if you have a deep class hierarchy with methods that are being overridden, or some are and some aren't. You can see exactly which methods. Okay, now look at these numbers on the side here. You can see the colouring here? The colouring is based on something called the, it's mad, median average deviation, I think. That's looking at the numbers for all the calls in this file. So it's useful sometimes, but often it's distorted because a file will have many subroutines that may have different kind of characteristics. But generally speaking, if you're in a hurry, red is bad, green is good. So don't bother looking at the green stuff. So we spent an average of 1.08 milliseconds in each call here. Let's go back. Oh yes, so you can jump to all the files. So that's every file that got profiles. And down here is a list of all those files. And this list is ordered by the time spent executing statements in that file. Now, node.pm, which is the same file we looked at a moment ago, includes 3 string evals. Let's see if I can demonstrate string evals. Okay, so at the top of each source code file, you'll see the file name, summary of the statements, and here you have all the subroutines that are in that file. So this is a great place to start. You arrive at a file and you look, oh, right, you can kind of get a sense of where the hotspots are. And it labels recursion and tells you the depth. Do I have any string events? Okay, so here we have an eval. Now traditionally you haven't been able to profile the contents of a string eval. And I spent an insane amount of time, almost going insane, trying to make that work with NYTProf. And if we're really lucky. So basically there's 2 kinds of string evals that get executed multiple times. One of them executes the same code over and over again, and sometimes the string eval will be doing different code each time. NYTProf looks at the code of the string evals and says, if they look sufficiently similar, then I'm going to merge them. So let's have a look at this merged string eval. Now it puts up a big warning saying, hey, you know, all sorts of crazy things may have happened here because I've mashed together a whole bunch of data from different string evals. But in this case, it looks reasonably useful. So it's actually telling you, giving you sensible looking timing data for what happened inside the string eval. Now before NYTProf, it just wasn't possible to get insight into that kind of thing. Ooh, just for a laugh. Actually, that's probably not useful, but okay. Now I've got 23 minutes left, so I'm going to nip back here. There we are. What I want to do now is give you some sense of the order in which I would go about optimizing a piece of code. If somebody says, please make this code run faster, these are the kind of things that I think about in the order that I do them. Important to note that don't take any particular examples too literally. The details vary. It's important to do your own testing. Okay, this is one of my favourite examples. 2 is much slower than 1. Don't use 2s. There's a real problem here. Now, what's happening here is that the statement profiler just measures the time between starting one statement and starting the next statement. So the time for the 2 is the time between starting to execute the 2 and starting to execute what? The next statement, which in this case would be the for loop. It's re-evaluating the for loop condition. So the last statement in the loop is paying the price of the loop overheads. So just be a little cautious. That's an easy trap to fall into. You're looking at a piece of code and there's a block and the last thing in the block seems slow. Just pause for a moment and think, well, maybe it's not quite as obvious as it seems. Now here's an example, 2 identical pieces of code, and the second one's faster. What's happening here? Okay, what's happening here? CPU caching. Yeah. So the second time you call in the same thing, the CPU caches are all lined up to have just the data you want to use. So you have to kind of think a little more when you're looking at these things, that they're not obvious. There are plenty of traps to fall into. Okay, before you start, this is serious crack. It's easy to spend huge amounts of time playing with NYTProf. You know, you can spend far more time of your time than you will ever gain back by making the code faster, because it's so much fun. So, Michael Jackson, not the Michael Jackson, another one, said, don't do it. First of all, just don't do it. And second of all, don't do it yet. Put it off. Things may change, there's plenty of reasons. So, why not do it? More, as you read, so it's basically saying, you will do bad things in the name of performance. You will break all the rules that you would otherwise not break in the name of making your code faster. And that will have serious problems. There will be consequences. Now, Donald Knuth, you may know this quote, premature optimization is the root of all evil. But he also said, we should not pass up the opportunities in that critical 3%. So how do we do that? So, simple one, just throw hardware at it, make it faster. You know, throw more hardware, faster hardware. Don't mess with the software. If you can avoid messing with the software, that's great. Hardware upgrades are usually straightforward, risky. The hardware is always getting faster. Just throw hardware at it. If you need to look at the software, it's very important not to guess. We all kind of think we know where the program is going to be slow, but don't try to second guess it, prove it. And there's an old carpenter's phrase, measure twice, cut once. So before you change something, know why you're changing it. Have good reasons, have measurements. So, the things I do first. I pick a workload, something I'm going to ask the software to do that I understand well, a representative workload. So if it's a web server, for example, I'll pick one request that's representative, and I'll run that one request 1,000 times. So I know exactly the work that I've given it, and that it should be run 1,000 times. And then I look at the exclusive times and say, do they look reasonable? You know, is this a reasonable amount of time? And I can look at the worst offenders, fix the local problems, do it again. The great thing about this is that because you know you've given it 1,000 requests, you can see those things that are called 1,000 times and those things that are called 20,000 times. And you can say, hang on, is it reasonable for that to be called 20 times for each request? So the numbers jump out at you very easily. So fix the local simple problems, profile it again, is it fast enough? Stop. Now, simple local fixes. What are simple local fixes? They're things that are unlikely to introduce bugs. So this is a common one. You frequently see loops where there's something being calculated inside the loop that could be calculated outside the loop. Another one I see often is repeated chains of accessors within a loop. So use a temporary variable, excuse me. Faster accessors. Now a lot of work has gone into making accessors faster, so the kind of the modern Perl technology for this is good. I don't know what the current fastest is. There's a kind of a bit of a race between the competing modules. But usually there's often a drop-in replacement that's faster than the one you're using. Another common one I see is calling subroutines that don't do anything, and the typical case is logging. You know, there might be a lot of logging code, logging calls sprinkled throughout the code, and normally the logging is turned off. But you're calling the logging function, you're spending time gathering together the arguments to call the logging function with, and then the logging function says, logging's not turned on, and it returns. So if you can check up front whether your logging is turned on by checking somehow, then only calling the logging methods if logging is on, that's a simple saving. Another common thing I see is a lot of initializations at the beginning of a subroutine, and then checks to see whether the subroutine should do something useful. Well, if you move those checks above the initializations, that'll save you a bunch of work for those times when the subroutine doesn't need to do anything. And this is an actual diff from some production code that was very hot production code being called billions of times. And I made this change and it got a lot faster. You know, sometimes the code is just silly. Now, regular expressions can be tricky things to evaluate in terms of performance. Both because it's hard to predict how long it'll take, but also because certain data patterns can trigger pathological behaviours. Now, NYTProf now measures the time spent in the opcodes associated with regular expressions. So at least NYTProf will tell you if the regular expression is the cause of a problem. Now, another very common one is to avoid unpacking arguments in very hot subroutines. So if there's a way of avoiding copying the arguments into lexicals in a very short subroutine, that's often useful. So if you're delegating, just use underscore or shift or $_ square brackets. Okay. Now I'm looking at this and wondering why I'm looking at this. Yes, so it's an example for that previous slide. You can see the different timings. So here, 800 milliseconds, 800 milliseconds, 678. And here I'm not unpacking the arguments. So here I'm copying into a lexical via a list assignment. Here I'm doing shift, and here I'm not unpacking. Okay, capturing parentheses in regular expressions at extra cost. So, you've done all those things. They're all pretty simple, no big structural changes. You retest. Is it fast enough? Stop. Put the profiler down, walk away. Okay? Because if you don't, it's very tempting to go to the next stage, and then you start wanting to make deeper changes in the name of performance. So, here again I'm saying the same thing. So I think actually for that first example, that phase 1 stuff, you could throw any reasonable workload at it. This is the one where you want to do something very specific. Because with the 1,000 identical requests, you can now check the inclusive times. Yeah. So here, for example, we have the structure of the code that may be loading something, manipulating it, writing it out. You can see how much time is spent in each of those phases when you're looking top down. Subroutine call counts. If you know you've given it 1,000 requests or 1,000 lines, if it's something that processes line data, or 1,000 records, if it's a database-based software, you can say, are the call counts reasonable? Because any high counts usually identify somewhere where you might be able to use some caching, or there's poor logic, or things being calculated over and over again that don't need to be. Now, adding caching, very tempting. It's a great fix for many, many performance problems. But there's a big catch. Every time you add caching to a bit of software, you have to remember to invalidate the cache. You have to think about, how is this cache going to get invalidated? When will the content cease to be relevant? Because stale cache bugs can be really hard to pin down. So every time you're adding a cache, going, oh yeah, this will make it much faster, just think about the fact in 3 months' time you may spend a week debugging that cache you put in. Now you saw in the example I showed you of a report, it lists all the places that called into a subroutine and all the places that called out. All the places that called into a subroutine, they have links that you can chase up to where they're called from. So if you're thinking of adding caching, it's useful to walk up the call chain, looking for the most appropriate place to add the caching to, because it might not be that function that you're thinking is too slow and needs caching. It may be appropriate to add the caching higher up, because often it's easier to invalidate the cache if it's put higher up. Or sometimes you might want to drill down and find somewhere lower to put the cache. Now, another common problem is creating a lot of objects that don't get used. So a typical example here would be processing log files, or processing some kind of line-based data or record-based data. You're inflating the log records, or you're inflating the things coming from the database, and then maybe higher up in the code you're throwing most of them away. So you spent a lot of time creating objects that you then discard without using. So datetime is a good example of something that is often used to inflate values coming from log records or databases, but datetime is quite expensive. So there are various lightweight proxies like datetime, tiny, light, lazy, init, and there are other more general lightweight proxies that will work for any object. I once made a 25% improvement in a piece of software by making a one-line code change to use one of these. Think about reconfiguring your Perl. Usually that's a fairly safe option. You're not changing the logic of your application. Thread support in recent Perls has got a lot better, and maybe in recent operating systems too. The cost for a threaded versus a non-threaded Perl, I think, is now typically around 5%, but it varies depending on the version of the operating system, and the libraries, and the compiler, and da-da-da. Avoid building with debugging, with Perl debugging. It costs about 15%. Also, the malloc you use may be a significant factor. Perl does a lot of mallocs, you'd know if you saw my talk yesterday. Also, 64-bit, that has trade-offs, sometimes positive, sometimes negative. And if you're really looking for a quick fix to a big application, consider spending money on a commercial compiler. Some of the commercial compilers from people like Sun and Intel can actually make significant improvements in performance. Okay, upgrade your Perl. Always a good idea. Well, usually. Test first, of course. But Perl is getting faster. It's not only getting faster, but it's using less memory. So a lot of work has gone into fine-tuning the Perl internals in recent versions. Okay. Take a breath. Retest. Is it fast enough? Stop. Put the profiler down. Walk away. Because now we're going to do more evil things. Structural changes. So it's very common to have a list of something that you want to call a method on. So you have code like this. Walk the dog for all the dogs. Now you pay a price for every method call. And especially at the start of that method, it's going to be checking arguments and permissions and da-da-da. If you add a new method that will accept the array, you get rid of a whole bunch of overheads. So that's a relatively simple change. Sometimes a lot of code is using hashes just because that's kind of the default choice. But if the contents are quite simple, maybe an array would be useful. Or perhaps the other way around, changing from an array to a hash would simplify some of the code elsewhere. Think about the algorithm. Is the way you're approaching the problem a good way? Is there just a better solution, a better method? Sometimes there'll be some really hot spots, a little bit of logic that's called many times, millions of times, billions of times. You can often get a big boost by changing that to be written in C code. Inline C is a great way of doing it. It's worth looking at that first. I've used that a couple of times in production code, and it's worked out very well. I've heard people say there are deployment issues, because effectively the first time the code runs, after each change, it fires up a compiler, and maybe you don't want a compiler running on the production system, but worth a look. Sometimes when you're looking at a big application, you don't see anything obvious. Because time is spread out, and you think, what am I going to do? Well, little by little. Just make little changes, test them well, and bit by bit you'll start making improvements. Because as one bit gets faster, it makes it more obvious that there's a problem elsewhere, and you can make that bit faster. The bottlenecks shift. Okay, there's another talk there by Perrin Harkins that has some useful, more sort of application-focused suggestions. Okay. Any questions?
So, what next? How does NYTProf get even more better?
Even more better. Okay. So there's a problem internally NYTProf uses a clock that has a 100 nanosecond resolution. And it uses that 100 nanosecond resolution for counting statement times. Okay, and it measures the number of ticks. But for subroutines can often spend a long time, so it's easy to overflow the maximum count. So for the subroutine profiler uses a double precision floating point value. Now the problem is that for very fast subroutines, and that includes opcodes, the time spent is so small that you're down in the noisy part of the floating point precision. So what can happen is you accumulate a lot of errors. So the timing gets off. The more often it's called, the more the errors can accumulate. So you can end up with a subroutine that calls another subroutine many, many times, and the time spent in that subroutine making those calls is more than the time you spent in the subroutine that made the calls, which is obviously broken. So I plan to change the logic there. So where possible, it'll use a high precision for the subroutine timer as well. And that will make a lot of cases where the subroutine profiler seems to be saying something odd, especially about very high speed subroutines. It'll fix those.
100 nanoseconds?
100 nanoseconds.
NYTProf の中で使っているタイマーが、100ナノセカンドの、100ナノセカンド単位でカウントしているものなんですけども、すごく速い関数とかをそれで測っていくと、少しずつそこからオーバーフローが発生して、例えば全然桁が違う大きさの関数、オフ3の動きとかをそれで測っていくと、どんどん誤差が溜まっていって、それを呼び出している関数の、実行時間と、その速い関数オフ3とかの実行時間がうまく合わない場合が出てきて、そこで誤差がいろいろ生まれることなので、そういったものをこれから、もっと正確なタイマーを使って、測るようにしていくという予定があります。他に質問はないですか？はい。
Using NYTProf with Coro cause segmentation fault, will you solve it?
NYTProf をコーロードゲームに使うとセクフォルトを起こらしてるんです。それを直しております。
Coro is Coro is magic. And is very similar to threading, and is deeply embedded into, or attaches itself deeply into the Perl interpreter. So I would like to get NYTProf working with Coro. I would like to get NYTProf working with threads. But it's not a priority for me right now. Now, I think if NYTProf was fixed to work with threads, it would also work with Coro. And the work to make it work with threads isn't very complicated for somebody who's done that before. So I'd welcome volunteers.
コロは魔法なので、基本的には、どうしようもないということなんですけど、ただ、コロ自体はスレッドみたいなものなので、そのスレッドをサポートできるようになれば、コロもサポートできるはずと。でただ、それは今、自分のプライオリティ、優先のがあまり高くないので、もしパッチとかを送ってくれる方がいれば、すごくウェルカムな状態です。であと、スレッドに対する、処理、この直すことをやったことない人であれば、それほど難しいことないので、ぜひ、もし興味があったら協力してくださいということでした。時間があまりないんですけど、他に質問がある方いますか？大丈夫ですか？はい、じゃあありがとうございました。